So on the other day, we have done the external analysis. So while doing the external analysis, what we did is we selected this untitled, that is site level we have selected. From there, after that, we have given the boundary conditions, okay, and we have solved the problem and we have got the results. So that is external analysis. Okay, for external analysis, we go through the boundary conditions. Okay, so site boundary conditions. We give the boundary condition at the site. That means I have to select this if I want to do that, do the external CFD analysis. The same thing if I select the building or if I select the zone. Okay, so then it will become an internal analysis. So here, when I select the zone, here you can see where the various components of the zone itself. Okay, so already the room is there. Okay, several boundary conditions. I think already it is given for this problem. So we have a supply here. Okay, it is like a split AC. Okay, so from here the throw is there moving up, and here we are having a outflow or vent. Okay, outflow is there, and we have walls will be at low temperature. So or the temperature whatever it is given as per the boundary condition. So that will be there. Okay, so this is how domain will be there. So previously we did the meshing outside the building. Okay, so we did the meshing outside the building. Okay, now we will be doing the meshing inside the building or inside the room. Okay, so that is how we will be doing. Okay, so there are various types of boundary conditions, especially for inside. Okay, so that we have to see. Okay, the first one. First, I will take the problem. Okay, so now it is asking for a name for this analysis. Okay, so I don't give any name. Okay, so or I will give a internal. Okay, so I will give internal as a name. Okay, so it is asking speaking about the grid spacing. So I told that if you have the domain here in CFD, the domain is the air inside. But for energy simulation, the domain is the wall. Okay, all the walls, solids, everything put together. But for the CFD internal analysis, the domain is the air inside the, for example, conditioned air inside the room. So now I am going to split the conditioned air into number of subdivisions. So the grid spacing is given here. Okay, so here you can see the grid spacing. Okay, so I'm giving okay for the CFD analysis. Okay, so I'm getting the, so here if you want to see the grid, okay, if you want to see the grid or if you want to edit the grid, okay, so all these things it can be done. So okay, so here I have the edit the grid option is there. So here now you can see now the domain is divided into number of subdivisions. So here when I select the region, you have lot of blocks. Okay, so these blocks will be extending inside. So now it is showing in the wall only, but in reality these blocks will be extending inside also. Okay, so that we have to take. Okay, and okay, so now after okay, so after this, okay, so now we will yeah, so now we can go to the CFD analysis. Okay, CFD analysis. So here okay, so here you can give the various inputs. Okay, why I'm showing this tab is because all the concepts what we are going to discuss today. Okay, for example, turbulence model, discretization scheme, iterations. So all these things, isothermal, surface heat transfer, initial conditions, cell monitor, residual display. Okay, all these things we are going to discuss today, or some of them we would have discussed already. Okay, so all these things we are going to discuss today. Okay, so you can now monitor the residual for see right now it is showing the residual for mass. So that is continuity, x velocity, y velocity, z velocity. Okay, and you can even include the temperature also, because In the external flow, we will not be involving the energy equation. For internal flow, we will be involving the energy equation. Okay, so because of that, I'm enabling the temperature. I have to monitor the temperature residual. Okay, and for turbulence, I'm having turbulent kinetic energy equation and turbulent dissipation rate equation. All these concepts we are going to discuss today. So that's why I'm opening this tab and I'm showing. Okay, so we are going to study about the turbulence models, discretization scheme, iterations. Okay, so what about the initial conditions, how we are monitoring in the cell. Okay, so similarly, what is the residual display. Okay, so that's why I'm opening. So all these things, okay, we are not going to leave anything. Okay, so we are going to discuss everything. Even we are going to discuss about this monitor and X velocity. Okay, now we will start and one minute. Okay, yeah. So here just now we can edit the grid. Okay, so you can edit the grid. That is what we have seen. Okay, and the boundary conditions, it is already given to the problem. Okay, so whatever so what is the boundary condition? So if you are having a conditioned room, so inside that AC throw will be there. Similarly, outflow will be there. Wall will be at high temperature. So all these boundary conditions, it is given to the problem. Okay, so you can actually see the boundary conditions. Okay, so you can actually see the boundary conditions. That we will do it. Okay, that we will do it afterwards. Now we will run the calculation. Okay, so we will run the calculation. Otherwise, our discussion also, it will be getting delayed. Okay, so this is the thing. Okay, so this is the thing. So now we have created the domain. We have discretized that. We have meshed that, and after that we have given boundary conditions. Okay, temperature boundary conditions, flow inlet, flow outlet boundary conditions. So all these things we have given. Okay, so now we are starting the simulation. Okay, so I'm giving start the simulation. So here you can see, unlike a external CFD analysis, here it is fast. Okay, so it is fast here, and okay, so we will let it go. Okay, so now we will go for our discussion till it converges. Okay, because everything we have to see, it is related. The running of the solver is related to the today's discussion. So that is why. Okay, I think not saved. Okay, no problem. Okay. So we have discussed about the CFD. What are all the general steps? So what are all the how to get the overall equation? How to get the overall equation from the general transport equation? And after that, we have seen that how we get all the equations from a single equation, and how the equation will be in the vector form, and how the equation will be in the scalar form. So all these equations, I think we have had a detailed expression, discussions. Types of boundary conditions also we have discussed already. Okay, and how to do the discretization. Okay, that also we have discussed already. So we have found while discretizing right hand side diffusion terms, it will not pose any problem. Left hand side convection equations, convection algebraic equation, it will pose problem, especially when the velocity is high. So that is what we have seen. When velocity is high, you cannot use the central difference scheme. So you have to go for a upwind scheme only. Okay, you have to go for upwind scheme or power law scheme. Okay, or second order upwind scheme or quick scheme. Okay, and yeah. So I think this also you can see in the solver. Okay, the discretization scheme here you can see upwind hybrid power law. So upwind is the basic scheme whatever we have studied already. Hybrid scheme, I think that also we have. Okay, I will tell you about that. Okay, power law scheme we have studied already. Okay, so now the solution is converged. Okay, now the solution is converged. Okay, Now I have to tell about the hybrid scheme. So hybrid scheme is a very simple scheme. I didn't discuss that. Maybe now we can have a small discussion on hybrid scheme. Okay, so we have discussed about central difference scheme and upwind scheme. Okay, what is central difference scheme? So whenever you want the for convection discretization, whenever you want the face value E, so what you will do, it you will take average of these two. Okay, so you will take 5p plus 5e divided by 2. Okay, similarly whenever you are having a whenever you are having this uh, uh, whenever you are having a higher velocity, okay, so higher when Peclet number is greater than 2, so you will be going for the first order upwind scheme. Okay, so when Peclet number is less than 2, so you go for central differencing scheme. There is no trouble. When Peclet number is more, we are going for first order upwind scheme. You give whatever I told orally now, you write it in the form of algorithm. So you know if and if statement, you know if Peclet number is greater than 2, go to uh, a first order upwind scheme. Okay, if Peclet number less than 2, go for central difference scheme. So that is how we will be using. Okay, if you use like that, so that is called hybrid scheme. Very simple. Okay, so um, when calculate the Peclet number first. What is Peclet number? The ratio of convection to diffusion. So it is rho u convection coefficient by delta L, or rho u delta L by convection coefficient. Sorry, diffusion coefficient. Rho u L divided by diffusion coefficient. So this you calculate first. If the value is less than 2, okay, then you go for central difference scheme. If the value is greater than 2, then you go for uh, uh, upwind scheme. Okay, if the value is less than 2, go for central difference scheme. If the value is greater than 2, then you go for upwind scheme. Okay, so this is called as hybrid scheme. So that means so this point now you have understood. Okay, so this point which you are using in the solver, discretization scheme. So what is a discretization scheme? So discretization scheme is the one which we will be using for convection. Okay, so lower velocities or at lower Peclet number or lower convection, so we will be going by central difference scheme. So that is default. Okay, if Peclet number is greater than 2, we will go for hybrid scheme. Okay, so Peclet number is greater than 2, we will be going for upwind scheme. And if both the case, if Peclet number is less than 2, if you go for central difference, and greater than 2 if you go for upwind scheme. So that is called hybrid scheme. Okay, what is power law scheme? So that we have discussed in the last class. So in the power law, we will be uh, interpolating based on the polynomial, exact polynomial solution. Okay, so we will be interpolating based on exact polynomial solution. So that means you will be calculating the uh, uh, you will be calculating the Peclet number. Okay, so up to 10 Peclet number 10. Okay, you can use power law scheme, and after that you can use upwind scheme. So this also we have discussed in the last class. Okay, so why am so that means discretization scheme convection is very important. Okay, so that's why it is given separately. So now we have completed one. Okay, so where we are going for discretization scheme? So in the discretization scheme, we are going for convection only. So you go for convection and diffusion. Okay, so you go for convection and diffusion. Okay, yeah. So this one. So when you go for convection and diffusion, so diffusion will not pose any problem. Convection alone, it will pose problem. Okay, so there what you have to do, so you have to go for interpolation. Okay, so whenever you are taking the face value, so you have to go for interpolation. So in the solver, what we have, okay, in the design builder solver, what we have, whatever it is given, it is just the you have power law scheme, then I have upwind scheme, then I have hybrid scheme. Okay, so only 3 schemes are given, but we have studied more schemes. Okay, no problem. Okay, so the next thing is okay, we will go back to the design builder and we will just post process and see. And one thing we have seen, the residue, you can see as I am iterating. Last class I told you, so we will be going for iterative procedure. two type of iterative procedures are possible. One iterative procedure is the uh, uh, Gauss-Jacobi method. The other iterative procedure is Gauss-Seidel method. Okay, in Gauss-Jacobi method, we will be having the initial condition. So initial condition means it is the initial Gus value. Okay, so here you can see what is the initial condition. It is not a time initial condition. When you are going for an iterative method, it is not a time initiative condition, but it is the initial solution. So here it is given in the form of initial condition. But we are not solving a transient problem. We are solving a steady state problem. So what is the meaning of that? It means that you have to have the initial solution. So that means throughout the domain, I'm giving the x velocity. That is for momentum equation. So throughout the domain, I'm giving for y velocity. Okay. So the y momentum equation. So that means I'm giving solution for y momentum equation. Throughout the domain, I'm giving z velocity. So that means I'm throughout the domain, I'm giving a value for y z momentum equation. And for energy equation throughout the domain, I'm giving initial temperature. Okay. So initial temperature means so these are all Gus value where it will be starting. Okay. So similarly for turbulent dissipation rate also it is given. So that means what I told we will be solving turbulent kinetic energy equation and turbulent dissipation equation also. So this class we are going to discuss about the turbulent kinetic energy and the turbulent dissipation in detail. Okay. So that means for that also we are having boundary condition. So only one is given. If one is given, the other thing can be calculated. For example, dissipation, from dissipation rate, you can calculate what is the turbulent kinetic energy. Because the turbulent kinetic energy is small k, okay, but turbulent dissipation rate is dk by dt. So from that, okay, so you can calculate when this is given, you can integrate that and you can find out what is turbulent kinetic energy. So that is what. So now you have understood what is initial condition. So initial condition means that it is the initial solution. So that means at this point, whatever the values you are giving, okay. So that is so initial solution when you are giving, so it is not going to be accurate. Okay, so it is going to be approximate only. So because of that, what happens? The residue will be higher. So as the iteration proceeds, what will happen? The residue value, okay, the residue value will be decreasing. When the residue value is going less than 10 power minus 5, so here it is given as 10 power minus 5 is given as 0. So that is why when all the equations, when it is reaching 10 power minus 5, what is happening? It is telling that the solution is converged. So that means what is our convergence criteria, or what is our zero definition? So our zero definition is 10 power minus 5 only. Okay, so I told you. Okay, and similarly, we don't know whether the solution has converged or not. Okay, suppose if I am putting 10 power minus 3, so you will find that the solution might have not converged. So it will be somewhere here only. Okay, but for monitoring the solution, how you can monitoring the solution? By monitoring the variable in the domain. What is our domain? Our domain is the room under consideration. For that room only we are doing this analysis. Okay, so for that room, okay, so for that room we are considering one point inside the room, and when we are starting the iteration, the error is very much higher. So here you can see for x velocity where you are starting. X velocity you are starting from 0. So from 0 it is iterating. So that means it is fluctuating. You can see the value is going down, and again it is rising. Okay, and after that also it is, you are not having the correct value. Then it is coming down and then it is stabilizing. So now here you are saying the velocity you are having it as minus 0.006. Okay, minus 0.05. But that is not varying with respect to iteration. Okay, so then only you can say that your solution is converged. Okay, so for convergence of the solution, you monitoring two things. One is the residual, the other one is you are monitoring the x velocity. Okay, so that is what we have to do. So here you can see when we are going for monitoring the solution. Okay, so last class we have seen after completing the discretization. That now we have seen, now we have done the discretization. So the full domain was there. We have divided the domain into small pieces. For each domain, I am writing the I'm having the governing differential equation, which is in the partial differential form. I am converting that partial differential equation into algebraic equation. So that means how many number of mesh is there, so many number of algebraic equations will be there. Or in other words, how many number of meshes there, so many number of solutions will be there. So that means this is our solution matrix. So this is boundary condition matrix. All of you might be knowing. This is boundary condition vector. Okay, so here this is solution vector, and this is material matrix. Okay, this is material matrix. So that means this is our solution. How many number of solutions will be there? How many number of meshes are there? So many number of solutions will be there. Okay, so that means how many number of meshes there inside them? So many number of turn will be there. So that is what we have to understand. So that means when you are going for iterative solution, so you need not write it in the matrix form like this. Okay, just you can write it in this form itself. That is sufficient. So whatever the value you are going to calculate. Okay, so for example here 1 1, so will be the value you will be calculating. So that you have to put it in the left. Okay, and the next I will be having 2 2. So that also. So likewise you can do 3 3 4 4 5 5. You can put all this value in the left. The balance things you can put it on the right hand side. Okay, so the balance things I can put it on the right hand side. So that is how you will be doing the iteration. So I think I have shown you about iteration for the Gauss-Seidel method. 2 classes before I shown you how to do the iteration for the Gauss-Seidel method. Okay, so this is how the equation will be. So the general form of equation will be like this only. Okay, so the left hand side I will be having AP phi p, right hand side I will be having A and B phi and B plus B. Okay, so the residue, what I have to do, so this value minus of this. So this I have to put it in the modular form. This I have to put it in the modular form. Okay, so this is the residue. So this I call it as the residue. So AP phi p minus of summation A and B, B minus B. So this is the residue. Just now you have seen the residue. Residue initially it was higher, then it was decreasing. So what is the residue? You have the partial differential equation. I bring all the terms on left hand side. Right hand side will be 0. Similarly, you are converting the partial differential equation into algebraic equation. So that means that algebraic equation also, you bring all the term to the left hand side, right hand side it should be equal to 0. Okay, so that is what I am bringing all the terms in the algebraic equation on one side. So this should be equal to 0. But when I am giving the approximate solution, it will not be equal to 0. When I am giving approximate solution, it will not be equal to 0. So it will be equal to some value. So that is called as the residue value. Okay. So now whatever you have watched, so that is the residue value. Okay, so that is the residue value. Okay, so here, okay, so here whatever you have watched, so this is the residue value. So you are having a residue for all the equations. So that is algebraic equation. It should be equal to 0. When I am substituting, it will not be equal to 0. So that means it is having some residue. So that residue is only it is given. So what is that you have to do? So I have to make that residue equal to 0. So how I can make that residue is equal to 0? So I have to iterate. Okay, so I have to iterate again and again to correct solution so that that residue will be equal to 0. But you know the residue can be what is 0? That I have to define. 10 power minus 3 can be 0, 10 power minus 5 can be 0, 10 power minus 25 can be 0 also. But you cannot go on like that. Okay. So for you, what is important? You should have a constant value as the solution. So that is what is required. So for that, how much you have to run, that much you can run. Okay. So here you are seeing at the 10 power minus 5, you are getting a constant value in the domain. So that means that is sufficient. So that is why I'm giving a 10 power minus 5 as my 0 criterion. So that is called as convergence criteria. Okay. So that's what we have to understand. Okay. And after that, okay, so we can iterate by Jacobi method. Okay, so Jacobi, I give all the initial value. I go to the algebraic equation. I solve it. I get a new set. So then I will make that new set of solution as the Gus solution. Again, I have to solve the equations. Okay, so that is second iteration. So now I will get a new set that I have to take it as the initial condition. I have to solve it and then I have to get the solution. Okay, so like that if I do, okay, so that is called as iterative solution. So that is called the iterative Jacobi solution. So then if I am using the terms immediately, okay, so instead of having one set, okay, and getting next set and using it, I can use the values immediately in the next equations. For example, for one, if I'm calculating T1, I can use it in the next equation. When I'm calculating T2, this value I can use it. Similarly, when I'm calculating T3, new value of T1, T2, I can use it. So if I do that, it's called a Gauss-Seidel method. So that also you have to. So mostly in the solvers, Gauss-Seidel method only it will be used. Okay, Gauss-Seidel method with relaxation factor. Okay, successive over relaxation factor, it will be used. Okay, so successive over relaxation factor already I told you. So successive successive over relaxation factor or under relaxation factor, so it will be like this. Okay, so if you are iterating for okay, so you are starting with some temperature. Okay, so for example you are starting with 40 degrees. So when you are iterating, so suddenly or you think that you are starting with 20 degrees. So when you are iterating, okay, so you are getting some at one point in iteration, you are getting 30 value. 30 is the value. So when you are iterating, you are getting 31. Okay, so the next what you have to give, you have to give 31 as the value for that particular equation. But what you are if you are finding that if you give like that, the solution may not converge. Okay, so what you have to do on that point, instead of your present value is 30, the next value should be 31 as per Gauss-Seidel procedure. But instead of that, what you are doing, you are giving 30.1. Okay, because you are expecting that the solution will not converge, you are giving 30.1. So how you are doing that? 31 minus 30. Okay, so old value, fresh value minus old value, 31 minus 30, that is 1 degree. So in that I multiply by 10% or 0.1. So what I get, 1 into 0.1, it will become 0.1. So I give 30.1. Okay, so that is how I am ending. So the latest value, it is this is like 31, this is 30. Okay, so I have 1, the difference is 1. So this is again 30. So now this is 0.1. Okay, the under relaxation factor is 0.1. So what happens? So in next value, I will not be giving 31, I will be getting 30.1. So you may ask why I have to do like that. So in some problem, okay, so when you mark when your step size is very smaller into the iterative procedure, you will be getting a solution without any problem. If your step size is longer, you may not get the solution. Okay, so for cases like that only, you have to reduce the relaxation factor. So this is the relaxation factor. Okay, so here if you want, so in the best form, so this is the best form. So that means whatever the value you are getting in the Gauss-Seidel iterative procedure, new value, this is the old value. So when I subtract, okay, so like, this is like 1 degree. So this is the under relaxation factor. Okay, so if under relaxation factor is less, what is the advantage? Your speed of convergence will be lesser, but you will be getting a stable solution. Okay, but if you are going for increased value, so that is also possible. Okay, sometimes your solution will be very constant only, it may not be converging. Okay, so in that case you can even increase the relaxation factor. So that is called over relaxation. If u is greater than 1, it is over relaxation. So that means what? So here it will be 31, if this here it will be 30. Now you want to increase it, you want to increase the step size. So what you do, so this you can give it as a 2 or 3. So if you give this as 2, what will happen? So next the present value is 30, next value is 31. Instead of going in step size of 1, so it should go to 31. Now what it will go, since this over relaxation factor is 2, so now it will go as 32. So from 30 it will go as 32. So next, if you are getting another value, okay, for example, if you are getting you are giving 32, you are getting 33. Okay, so 33 as the next step value. So again multiply by 2. Okay, so what you will be getting 1 multiplied by 2. Okay, so then it will become 34. So now you will give 34. So that means now you are jumping. Okay, in the previous case you are restricting. Okay, but now in the over relaxation factor you are jumping. Okay, because the solution is not converging, so that is why you are jumping. So you are want to accelerate the convergence, so that's why you are jumping. For jumping you are taking a over relaxation factor. For restricting you are using under relaxation factor. Why you will restrict? You suspect you will not have convergence. Okay, so then you will have you will use under relaxation factor. You suspect there will be convergence. Okay, if you suspect that uh, uh, your solution will not converge, then you can use for over relaxation factor. And if you are not at all, if you are making this as 1, what will happen? You know, this and this will cancel. So what this is, that will become Gauss-Seidel procedure. Whatever the value you are getting, so 30 you will be getting, next it will show 31, so you have to use 31. Okay, so that will happen when u becomes 1. Okay, so this is very important. Okay, so in CFD this is very important, most of us may not be knowing. In CFD, this is very this under relaxation and over relaxation factor. It's very, very important. In some cases, by reducing the under relaxation factor itself, you will be getting the solution. Okay, so that's why I say this is very important. Okay, okay. So now you have understood relaxation factor method of solving the problem. Okay, and what is the residue? Already we have seen that when I am putting algebraic equations. So for each node, we will be solving a several set of algebraic equations. For example, for our problem, for each node, we will be having continuity equation, momentum equation, 3 momentum equation, 1 energy equation, or K equation, 1 epsilon equation. So many equations will be there. That is what we are finding. Okay. So that means how many equations are there, so many residue will be there. So that's what we have to understand. So that means phi also it will change. For example, in the continuity it will become 1, for x momentum it will become u, for y momentum it will become v, and for the z momentum it will become w, and energy equation it will become t. Okay, for k epsilon model it will become small k, and epsilon it will become epsilon. So many algebraic equations are there. Okay, so that means when you are solving the problem, for each node you will have all these things. That is very important. For each node you will have all these things. So you have to calculate of magnitude of everything. Okay, so what is our purpose of iteration? So I have to make this residue equal to 0. Okay, so that is our purpose. Okay, so handling this residue, it will be a problem because the residue will be sometimes it will have some dramatic values. Okay, a very high value, very low value, that is possible. So handling that, it will be very difficult. So whenever you have this problem of getting some dramatic value for residue, what you can do is you can take a ratio with the diagonal coefficient. Okay, so that is AP5P. It is the diagonal coefficient or the coefficient which you are trying to calculate. Okay, so if you take the ratio of these two, so that is called a scaled residue. Okay, this is the equation. Just I am dividing with the magnitude of AP5P. So that's called scaled equation. So this will be like a definite value, which it will be in your control. It will not be like a dramatic value. So it will be like a definite value. So it will be under your control. And if you are smart enough, you will know that now you have seen in the residue only one curve is coming. For continuity, one curve is coming. For momentum, one x momentum, one curve is coming. For energy, one curve is coming. But in the domain, how many values are there? So now you have split the domain. Okay, so almost we have around we'll be having around 1 lakh divisions in our CFD problems. So that means 1 lakh nodes are there. So which residue you are calculating, which residue you are tracking? So that we have to think. So that means we are not tracking any single residue. We are tracking the sum of all the residues. That means this value, scaled residue, we are calculating for all the nodes. So it means it is a summation of all these values for all the cells. This is very important. This is for all the cells. So that is what we are having it as the residue. So now we can go back. Okay, so now we can go back. So this residue, whatever we are having here, so this is the summation of all the residues. Okay, so it means for all the nodes or for all the mesh, okay, it is the summation. So what is that we are calculating? So this is what we are calculating. Okay, so this is what we are calculating. Okay, and just now we have seen for our case the convergence value was 10 power minus 5, and so now the residue will be like this. Okay, so just don't see the residue alone, you have to see the variable value also. For example, if it is temperature, monitor the temperature, or if it is the velocity, monitor the velocity. Okay, so that is the best way. So that is what we have to see. So here they are monitoring the drag coefficient. So whatever may be the value, so you can monitor any variable. Okay, and what is that you have to see that mass balance is there, energy balance is there. Okay, so that physics you have to monitor. Okay, so whenever you are going for the solutions. Okay, and okay, so now before coming that, so now we will go back to our solution, and now we will see the plots. Okay, so now what are the things we have seen? Okay, now we are turbulence modeling, we have not seen. Discretization we have seen. Okay, we have seen. So now for our case, we have taken a point. Iteration. Okay, now you are you know what is iteration. Okay, Gauss-Seidel iteration. How many number of iterations? It is maximum. Okay, it is maximum. So after that, again it will ask again, you have to iterate. That's it. Okay, so here how many iterations it has gone? It has gone up to 1,500 iterations. That's it. but we have given up to 5,000 iterations. Okay, so here you can see up to 5,000 iterations it can run. Okay, so and now our problem is not isothermal. Okay, because isothermal means at constant temperature. Yesterday problem it can be approximated as isothermal because we have not taken energy equation. Even that it is not isothermal. We have not considered the energy equation. There will not be any solution. So that means it is like isothermal. Okay, and it is how we are going to calculate the surface heat transfer. Okay, only from the simulation. Okay, so that is from the calculator only we can. But there is provision that we can give external values also, user defined values also we can give it. Initial continuation is the initial approximate solution for all the variables. For x momentum, y momentum, z momentum, initial temperature, initial dissipation rate, and even initial pressure also, pressure correction also we have to give. That is not given here. But in standard solvers, everything will be given. Pressure also you only have to give. Pressure correction also you have to give. And anything, whatever the variables that are involved, everything you have to give. Okay, what is cell monitor? Cell monitor, it is inside the domain, you will select some point. There you will monitor the variable. So what is the variable you are taking here? It is the x velocity. So here you can see we are monitoring the x velocity only. If the value of x velocity becomes constant, so it means that that is correct. Okay, if the value of x velocity is constant, so that means you are getting a constant value. So that means the solution has become iteration independent. Okay, so that means you can. So that's why we are monitoring the cell. Which cell you are monitoring? That also you have to see inside the domain. So we are having so many cells. So inside the domain, it is taking one center point. Okay, so if you want, you can see one center point will be there. So that it is taking and it is monitoring. And the residual display, just now I shown you. So this is the display. Before that, it was not showing the turbine kinetic energy, temperature, and the dissipation rate and all. I included just to explain to you what are all the equations it is solving and how it is solving. Okay. Okay. So these are the things, important things that I wanted to tell you. Now we will go to check the solution. Okay. So we can, since the solution is converged. Okay. So I'll close that. Now you know how to find the solution. So before that, we will select the thing. So I will go for slice setting. Okay, so it is giving velocity vector. I don't want vector. So I will go for field temperature and field velocity. Okay, so I'll first we will go for field velocity. Okay, then we will go for first you select that, then only that corresponding thing it will be there. Okay, so now let us see the velocity. I will put a cut here. Okay, why I'm putting a cut here? Because you are seeing that a throw is there. Okay, so fluid throw is there in this place, and I will put one more cut here. Okay, here a slight movement is there. Okay, sound movement of fluid is there in this direction, and if you want to have a cut in this direction, so there also we can see how it is. So if you want, you can turn that and you can see. Okay, so I'm turning that. So here you are finding that you are having a higher velocity here. I'm having a higher velocity here. Okay, and I am having the lower velocity in this way. So that means since the throw is from bottom to, so here you can see now boundary condition you are seeing it is throwing up. It is throwing up. So you are having a high velocity here. Blue color I told already it is low velocity. Okay, it's low velocity, and so I think so this is what we have to see. The next is you can see the temperature plot, field temperature plot. Why I'm selecting all these things? Because it is easy for you to look, because you are watching from a smaller screen, so it will be easy for you. Okay, cancel the orbiter. So now we are monitoring the temperature. Okay. So this is the temperature plot, and this I can put it in this direction also. Okay, so this is the temperature plot. Okay, field temperature contours. Okay, so here okay, so I'll put in this plant only we have the throw. Okay, so here you can see a high temperature is there here, and similarly I think it is a heater arrangement, so that is why we are having it like this. Okay, so this is like a heater arrangement, so hot air is coming. Okay, and this body, okay, so whatever it is kept here. Okay, So that body is hot, so that's why it is heat is radiating from that. Similarly, I think you can you can put a cut here also, and then you can see. Okay, I will remove this, and I will put a cut here. Okay, I will put a cut here. Now here you can see. Here also we have a high temperature. Okay, so here also I'm having a high temperature. Here also I am having a high temperature. So here I am having high temperature. Near that wall also I am having that temperature. So that means from the high temperature it is radiating into the, from this high temperature it is radiating into the room. Okay. Okay. So this is how we will be having the CFD analysis. Okay. And even there are provision. Okay. There are provision for measuring the comfort indices also. Okay. So even there is a provision for measuring the comfort indices also. So yeah. So 1 minute. Yeah. So you can calculate already the value is less, so it is converts. Similarly, you can calculate the other indices. Okay, so it is close. Okay, so I am updating the comfort indices. Okay, for that I have to give for these things we will study tomorrow. Just we will have a look. Okay. Can calculate the comfort indices just to know that how comfort indices will be plotted. Okay, now I am writing or updating the comfort indices. Now, so far you would have found only temperature, pressure, and velocity. Okay. So far we have found that only temperature, pressure, and velocity. Now you can find some new parameters will be included. Okay. So yeah. So yeah, here you can see some PMV is there, PPD contour is there, mean radiant temperature, operative temperature. I think these things we have come across already. So now after doing this comfort calculation only, now these contours are there. So now you can calculate what is PMV. Okay, so you can get the plot of PMV taper domain. So now I think one more thing is also on. Filter temperature is on, and even velocity is also on. Velocity vector is on. So I remove that, and I remove the slice. Okay, so it is in vector form PMV contours. So okay, field PMV contours will go. Then only you can see this. I can see, but I don't know whether you can see or not. Okay, so I'll go for filter. I'll remove this. Okay, remove all the slides. Now here you can see. So this is PMV contours. It will be varying from -3 to +3. Okay, I think it is going up to 5.25. Okay, so this value. Okay, so this is a health or it is a comfort parameter index. Okay, so regarding this we will be studying tomorrow. But now you please try to know that you can. It is possible for us to calculate uh, the parameters. That means comfort indices parameters, even PPD. Okay, so this is also one more parameter. So that also we can calculate. So with this small introduction, we will close here, and we will go for our discussion. Okay, so we will go for our discussion. Okay, now I think I have introduced to you what are all the various topics in the solver. Okay, so I told you about the what is convergence, what is residue, what is the variable, what is the solution of the variable. So all these things we have discussed. Okay, and what are all the properties of the discretization scheme. So properties of the discretization scheme, it is conservativeness. So you know, if it is the conservativeness should be there in the property, so then only you will be having global conservation. Okay, what is global conservation? Whatever the equations we are solving, all are conservative equations only. Okay, so that means at the lower level also, at the mesh level also, this conservation should be satisfied. Okay, So that is what is called as conservativeness. Okay, so whatever the discretization scheme you are using, it should have the property called as conservativeness. Okay. Next is boundedness. What is boundedness? So boundedness is also called as stability. So whenever you are trying to solve a problem using iterative method, okay, so or even a transient method also. So when you will have stability, so the simple method for understanding the stability is if you are having the domain, okay. So inside the domain, okay, inside the domain, inside the domain you will give the a lot of boundary inputs, okay. So the values that you are calculating inside the domain, so that should be within the boundary condition. For example, left hand side you are giving 100 degrees, right hand side you are giving 30 degrees. Top 100 degrees, bottom 30 degrees. So it goes without saying that your value should be between 100 and 30 degrees only. Okay. So if you are getting, because in the boundary, the maximum is 100 and minimum is 30. But if you are getting a value like 150 and minus 10 and all, so it means that you are going out of the boundary. So that is called as unboundedness or instability. So when your iterative procedure is not having the boundedness property, that means if it is not having the stability, then naturally you will be getting values outside the limiter. Okay. So for example, if you are giving a 130, so you may be getting a value beyond 100 and you may be getting a value less than 30. So that is called as stability, and also it is called as boundedness. Okay. But the scheme, whatever you are using, it should be have the properties of boundedness. Okay. And next is transportiveness. Yes, transportiveness is also important. You know that in our domain there will be flow, and whenever flow is there, velocity will be there. So if you know that central difference scheme, you can use it for a diffusion problem without any trouble, because the diffusion problem by physics, it will transport the property equally in all the directions. Okay. Similarly, your central difference scheme also, it will transport the variable, okay, equally in all the directions. So that is what we have seen that. So that is why in central difference method, whenever you are writing, so it will be like AP 5P is equal to summation of neighboring nodes plus B. That is how you are going to get it. So what is the meaning of that? It means that the property will be transmitted equally to the neighbors. So for a diffusion problem, central difference scheme is okay. But when you are going for a convective problem, highly convective problem, so that means a high velocity flow, but the Peclet number is higher. So that means there you cannot have this. Okay, so there you cannot have this. So what you have to do there? So then you have to think of transportiveness. So that means what? When it is highly convective flow, the velocity is more, you should not go for central difference scheme. You should go for upwind scheme, or you should go for hybrid scheme, or you should go for power law scheme, whatever it is mentioned in now. Okay. So this properties you should know. Okay. So these properties you should know. Okay. These are the properties of numerical scheme. And whenever you are going for solving in CFD, so mostly you will be coming about compressible and incompressible flow solvers. So now whatever in building, you will not be having a compressible flow solver. So that is very important. This we have to understand. You may be asking, see, where we are using it is compressible. So why we are not using a compressible flow? See, at low pressure, okay, at low pressure or at low velocity, okay, the fluid will be behaving like an incompressible flow only. When a fluid will be behaving in a compressible manner, okay, only if Mach number is greater than 0.3. So what is approximately if Mach number is greater than 0.3, so the velocity will be greater than 30 meter per second, 30-40 meter per second. So at that velocity only, you will be having that compressibility effect. Or simply saying density variation will be visible in that place only. Okay. So that means in practical or in reality, so you will be having problems which will be less than this velocity only. Because for in air conditioning, we don't think of going beyond 10 meter per second. Sound problem will be there in the duct of the equipment. So that means you are operating with a very low velocity. So that means you can assume that your flow is incompressible. Okay. Okay. So that means for our problem, for all the simulation or for our whatever the CFD simulation shown here, the fluid is assumed to be incompressible. That means you are using incompressible flow solver only. Okay. So that's why we will be using simple algorithm only. We are not using compressible flow solver. Compressible flow solver, it is it is kept separately for high speed flow, for high Mach number flow, where the density variation will be very much higher. Okay. Okay. So what will happen if I'm going for compressible flow solver? There, the solution of this equations, it is not at all a problem, because you'll be having one continuity and three momentum, one energy equation. Okay. So that's what we are going to have. But in compressible flow solver, we will be solving everything in the transient form only, because in a compressible flow, density is an important parameter. When the density is an important parameter, how you can solve? So the density will be in the transient term of continuity. So that means if you want to get the density, that means you have to go for transient flow solvers only. So then what you have to do, uh, you have to go for coupled solvers. You have to solve it in a transient flow. Okay. Whenever you are solving, what are all the parameters you will be interested? You will be interested in getting the velocities, three velocities, so that you can get it from the momentum, three momentum equation. And density you will be getting from continuity equation. Temperature you will be getting from the energy equation. So what about pressure? So pressure for a compressible flow, you can get it from P is equal to rho RT, or P is equal to compressibility into rho RT. So from that you can get what is equation for pressure. So that means T is already you have calculated from the energy equation, rho you have calculated from density, sorry, continuity equation. So for each node, you can use this simple formula. P is equal to compressibility into rho RT. From that, you can calculate the pressure. So that means you can get the pressure plot also. Because in all the solvers, you will be interested in getting the density plot, pressure plot, velocity plot, and temperature plot. Okay. So for a compressible flow, you don't have any problem at all. When I come for incompressible flow, okay. So what is that we will be interested? We will be interested in velocity plot, pressure plot, and temperature plot. Okay, so velocity will get from the momentum equation, three momentum equation. Temperature will get from the energy equation. In the continuity, you don't have the pressure term. Okay, so then there will be problem. Okay, so you have to think how you are overcoming it. At least we should understand why we have trouble. Okay, so in continuity equation, we don't have pressure term. For incompressible flow, there is no equation for calculating pressure at each node. Like for compressible flow, we have P is equal to rho RT. For incompressible flow, we don't have that equation. How we are solving this problem? Okay, we are solving this problem by pressure velocity coupling. So we are coupling the pressure and velocity almost like a Bernoulli. Okay, so I'll tell you how it is done. Okay, so that means we have continuity equation extra. Using that only, we have to calculate the pressure. So that is what we are doing. So we are using the continuity equation for calculating the pressure. And how we are doing that? Okay, so we are doing the pressure velocity coupling. Okay, so how we are doing that? See, that is the procedure for simple. So in simple, what we are doing, we will be taking
Participants, kindly wait for a moment.
Hello. Am I audible? Hello.
Yes. Yes.
Yeah, the line got connected. Long back or just now? Jagarajan, is it long back or just now?
Just now, sir. 30 seconds or
Just
1
now,
minute.
then because I have to see the slides. Okay, so we have been discussing about
Okay, sir.
this slide. Is the screen is visible? I have to present now again. Okay. Okay. Okay, so this is how. Okay, so now already I told you what is happening in simple algorithm. So you are taking a cell. In that cell, if the flow is higher, okay, if you are taking a cell, in that cell, if the flow is higher, okay, then we are reducing the pressure. Similarly, in the cell, if the flow is more, okay, so I'm sorry, if the flow is less, then we are increasing the pressure. Okay, okay, it is getting disconnected again and taking 1 minute. Okay, I'm here only. Okay, no problem. Okay, so now, so that is how it's happening. Okay, so if flow is more, pressure is reduced compared to other cells. Similarly, if flow is less, pressure is increased compared to other cells. So that is a simple principle behind the simple algorithm. So how it is done? It is used by pressure correction equation. How this you are getting this equation? We are deriving it from the continuity equation. So that is a very big derivation. So I think you will not be interested. But the concept what we have to understand is that the pressure correction it is there here only. So here you can see this is pressure correction term. This B dash. Okay, so that is the source term. It will be there for continuity imbalance. So what is the meaning of continuity imbalance? So if this term becomes more, this will be reduced. Similarly, if this term becomes less, this will be increased. So that is what I called as pressure velocity coupling. Okay, and this is again I'm telling it is an iterative procedure. Okay, so this is not like energy balance and other things we are not doing. See, we are following a step. Okay, uh, which actually it is resembling Bernoulli, which will be useful for us to for the convergence faster. Okay, so we are following a step which will be useful for us for the convergence faster. Okay, so that is called as pressure correction method. Okay, so whatever I told here, okay, in the cell whatever it is happening, so that is given in the form of a equation. So I have B dash. Okay, so when B dash increases, this will decrease. Similarly, when B dash is decreasing, this will be increasing. So that's how we are correcting the pressure. Okay, so that is the principle behind a simple algorithm. So all our solution, whatever we have seen now, okay, or yesterday also, it is solved using a simple algorithm only. Again, I'm stressing it is incompressible flow algorithm only. No compressible flow. Don't think that since it is air is gas, so we will be using compressible flow algorithm. Wrong. Okay, so we will be using simple algorithm only. Okay. Okay, so we have several variants of simple algorithm, but here we are not following all the methods. We are using simple algorithm only. Okay. Okay, so just now we have seen about the finite volume method of solutions. So the simple algorithm, it is also called a segregated solver. Okay, so we are for the procedure is we come with the Gus properties. We are solving all the momentum equation. We are solving the pressure correction equation. Okay, so then we are solving all the energy balance, species balance, turbulence equation. Everything we are solving. So we check for convergence. Okay, so if convergence is there, we are stopping. Otherwise, we are doing. So this is now while solving our problem, we have followed this procedure. If this is not there, this is not in your scope. Okay, so this is for a transient problem. So if it is a transient problem, we will be solving it in the form of transient. But all the equations will be solved simultaneously. All the transient equations will be solved simultaneously, and finally we will be solving the turbulence equations. Okay, and there is a time restriction because of stability. So that is called Courant Frederick Lewis condition. Okay, so Courant Frederick Lewis. Okay, so the number is L delta T divided by U. Okay, so that's what we are having. Okay, so uh, so we will be using that for the stability. If that value, if this value is greater than this, so then you will be getting an unstable result. Okay, let us learn about that. No problem. Okay, so this is for a compressible flow solver. Okay, and if it is going to be an unsteady flow solver, we are going to follow the compressible algorithm within each time step. Okay, each time step we will be following the we are going to for iterative procedure, and if it is converged, then the loop will go to the next time step. Okay, so that is how it is going to. And somewhere we will be coming out, we will be using multi-grid solver. So even for our solution also we will be using multi-grid solver. So what is multi-grid solver, or why we are going for a multi-grid solver? Okay, so these equations, okay, this will be solved for all the domain. Okay, so throughout the domain for that means the five algebraic equations per node we will be solving. So that's what we'll be doing. So while solving, there will be short wavelength errors as well as long wavelength errors. Okay, so these errors, okay, so it has to be minimized. So how it can be minimized? Okay, so long wavelength errors will be reduced in the coarse mesh. That is the concept. Similarly, short wavelength errors will be reduced in the finest mesh. So in this short wavelength lengths will, errors will be reduced. In the coarse mesh, you have a long wavelength errors will be reduced. So what you have to do? So for faster convergence, so you will be solving the CFD problem in the coarse mesh as well as the fine mesh. So we will be solving it for the coarse mesh as well as we will be solving it for the fine mesh. Okay. So why? Okay. So if I say about short wavelength error and long wavelength error, so these are all technical terms. I will tell you in a most simplest way what this multi-grid solver it is doing. So you will be solving the problem. Okay. So first the same problem you will be solving in coarse grid, then you will be solving it in the fine grid. So that is what we are doing. So what is the advantage of solving in the coarse grid and as well as in the, so in this problem all my boundary conditions will be there at the edge only, okay, at the boundary only. Now if I am solving it in the coarse grid, now my boundary conditions has entered inside the domain. So this is not clear. So here you can see along the surface, all along the surface boundary conditions are there. Now if I am solving in the coarse grid, so I'll be getting solutions here, all the grid points are the mesh, I'll be getting the solution. So what is the meaning of that? The solution has penetrated into the domain very faster now. Now if I'm going to solve with the original grid, it is going to take a very short time only. Okay, that is the concept. Okay, and suppose if I'm not doing this, I'm just going with this alone from the beginning to the end. Now what will happen? The whatever the boundary conditions that are there at the boundary surface of the domain, it will be penetrating slowly into the full domain, into the volume. So that is why it will take very long time. Okay, so this is the simple form of understanding what is a multi-grid solver is doing. Technically it is short wavelength are reduced at the finest mesh and long wavelength errors are reduced in the coarse mesh. Okay, so there will be a very big discussion for this, but simply, okay, what you can understand is the values are taken into the domain faster, so that is why the solution is faster. Okay, so this is called the multi-grid solver. So the you might have studied about AMG, that is algebraic multi-grid solvers. Okay, so that is what we will be using. Okay, so there is something called as geometric multi-grid solving also, that also it is used. Okay, some cases. Okay, so now we have discussed about the modeling. Okay, so that is the CFD modeling. So that was our ultimate intention. And in this solving, so there was two things which we have not done. Okay, so that is what we have is the turbulence model. Okay, so here turbulence model is there here. Okay, so two k epsilon and the constant effective velocity. So the two models are there. Okay, so what is this model and how we have to understand this model? So that is what we are going to have the next discussion. It is going to be a very short discussion only. I'll just make you to understand. That's it. Okay. So whenever you are having a boundary layer, so you'll be having a laminar boundary layer and you will be having a turbulent boundary layer. So it depends on the Reynolds number. Basically, it depends on the Reynolds number. When the Reynolds number for a flat plate, if it is greater than 5 into 10 power 5, you will be having a turbulence. Similarly, if Reynolds number, if it is greater than 20,000 for an flow over an obstacle, I'm going to have turbulence. Similarly, for internal flow, if it is greater than 2200, okay, so I'm going to turbulence. Even in natural convection also, if Rayleigh number is greater than 10 power 8, okay, so I'm going to have turbulence, okay. So that means there is some parameter, okay, so that beyond which you will be having turbulence. You should not tell only velocity. It is combination of velocity, density, and dynamic viscosity, okay. So that is what we have to understand. So the flow in the laminar layer, it is very simple for us to understand. But in the flow in the turbulent layer, so if I'm having a wall, okay, at the rear end of the bounded layer, so you'll be having the structure of the turbulent bounded layer will be like this. What is how the values will be? So for example, if I'm having a constant value in the laminar bounded layer, okay, the value will be constant over time. But when I'm coming to the turbulent bounded layer, near the wall or near the wall, okay, so I'll be having small fluctuations in the property. So that means if you are measuring temperature, temperature will be fluctuating like this here. Similarly, velocity, it will be fluctuating. Pressure, that also will be fluctuating. When I am going into the next layer, from the buffer layer, or I go for some distance, I'll be having a fully turbulent region or log layer. So there, if you find the same place, you will find that the amplitude of turbulence will be very much higher. Okay, so the amplitude of fluctuation, it will be very much higher. So that means the property, there will be large fluctuation in the properties. Okay, inside the turbulent core. Okay, so this I call it as turbulent core. Then again in the outer layer, the intensity of the turbulence will be lesser. Okay, but why that near the wall your the turbulent fluctuation is smaller? It is because of the viscous effect. Because you know near the wall the viscosity, okay, the viscous effects will be higher. That means the shear stress, okay, that will be maximum. So because of that, it will be trying to dampen the turbulence. So that is what you are finding. You are seeing the original signal here. Here you are seeing a dampened signal here. So put this in your mind. We are going to discuss that also. Okay. So the original turbulent signal is like this here. Your dampened signal is like this here. Okay. So now when you are going for solving the problem, so what is that you are interested? You want to know what is the effect of this on the flow field. That is what I am interested. So what is the effect of this turbulent fluctuations in the flow field? Okay, so that is what we are interested. Okay, so that means this is how we are going to have the turbulence. Okay, so if in the turbulent field, so the properties it is going to vary. So like how you have in the transport equation, phi as the general parameter for properties. So I'm telling that all the properties will be varying. That means what? Velocities will be varying, temperature will be varying, pressure also it will be fluctuating, not varying, fluctuating. Okay. So this fluctuation, you can see if the fluctuations are very much smaller. Okay, if the fluctuations are very much smaller, so then I can say that it is. Okay, 1 minute. I will just put it in the board so that just be with me for a few minutes. Otherwise, it will be very difficult. So it's taking some time. Okay, let it go. So if the amplitude of fluctuation is smaller, okay, so that means if it is like this, okay, that is also turbulence. But now that intensity is smaller, and now here you can see the intensity is more. Suppose if the fluctuation is like this, so that means now the intensity is very much higher. Okay, so that means the intensity of the turbulence it is given by the amplitude of phi dash. Okay, a small variation. Okay, so that means it is smaller, a larger variation. Okay, so that means the turbulence is more. Okay, but even for smaller fluctuation also this will be the same mean, and this also it will be same mean. Even if it is varying like this also, the mean will be same. So mean will not tell about the intensity of turbulence. Phi dash will tell about the intensity of turbulence. What is phi dash? It is fluctuation with respect to time. Okay, property fluctuation with respect to time, that will tell you what will be the amplitude of the turbulence or what will be the intensity of the turbulence. But handling phi dash should be a problem. Why? Because phi dash it is a fluctuation. So here it is given in the form of velocity. Okay. So what is mean? So up to this it is mean. I take average of these fluctuations. So that is phi bar. That is mean. So phi dash it is above that. Okay. Phi dash is above that. Okay. So now when I try to find the what is phi mean of this fluctuation. Okay. So how I to do? So I have to go for time integration. Okay, so that means 0 to delta t 5 t dt 1 by delta t. So that is I have to do. So that means I have to do the integration of this. Okay, but you know when I do the integration of that, okay, so I will be getting phi of t. Okay, next I can do the same thing for phi dash also. This is for phi of t. I am doing the integration. So that means I will get this area below that. Okay. Now, if I do that for phi dash alone, so you will find that it will be equal to 0. Okay. Why it will become 0? Because it is common sense. Because it is a fluctuation. Whenever plus fluctuation is there, minus fluctuation, it will follow the minus fluctuation. Similarly, see here you can see 2 plus is there, 2 minus is there. Again 2 plus, 2 minus. So that means every time plus is there, minus also will be followed. So it will be natural. It will be cancelling. Okay. So that means if I integrate this, okay, when I integrate this curve, forget about below portion. If I do the integration, this, it is like integrating the sine curve for the limit 0 to 2 pi. If I integrate the sine curve for the limit 0 to 2 pi, you know, it is 0 because the plus portion will cancel with the minus portion. Similarly, if I integrate this fluctuation also, it will become 0. So that is what you have to understand. So the solution for that is like what we do for sine wave. Even for sine wave, for studying the sine wave, what we are doing? We are using RMS. What is RMS? Root mean square. So I have to square the fluctuation. So that means when I square the fluctuations, all these fluctuations will become positive. That means it will become a bigger value like this. Then you take the root. So that means then you will get what will be the amplitude of this fluctuation. So everything will be positive value. So that is why we are going for RMS. So RMS of the fluctuation will give you the turbulence intensity. If I am having a small wave like this, very nearer, then RMS of the fluctuation will be smaller. If I'm having a bigger wave, then the RMS of fluctuation will be very much higher. So that means this RMS of fluctuation, it will tell you something about the turbulent intensity. Okay, that is point number 1. Similarly, the turbulent intensity you can find out by one more parameter called as turbulent kinetic energy. So what is turbulent kinetic energy? It is U dash square, V dash square, W dash square divided by 2. What is the meaning of that? It is turbulent kinetic energy per unit mass. If it is mv square, it is going to be kinetic energy. So m is not there. So then it is per unit mass. And the velocity is turbulent velocity. It is fluctuations in the x direction, y direction, and the z direction. So everything if I am squaring, I am getting a turbulent kinetic energy. So that is u dash square plus v dash square plus w dash square divided by 2. So this is a turbulent fluctuation. Okay. So this also will give the turbulent intensity. So that's why we are taking that parameter. Okay. K epsilon model. What is K epsilon model? Turbulent kinetic energy. What is turbulent kinetic energy? If the fluctuation is less, there is less turbulent kinetic energy. If the fluctuation is more, then more turbulent kinetic energy. What is the meaning of that? It tells you about the intensity of the turbulence. Similarly, the turbulent intensity, it can be given in one more form also, like a non-dimensional form, 2 by 3 k root k. K is velocity square. If I am taking root k, it is velocity. So velocity divided by u reference. So it is a non-dimensional turbulent intensity. It's a non-dimensional. So these are all the possible ways by which you can give the turbulence intensity to your problem. For example, if I'm having a problem, in that I have to tell whether it is less turbulent, medium turbulence, or high turbulence. How I can tell that? So I can tell that by turbulence intensity, turbulent kinetic energy, or by RMS of the turbulent fluctuations. Okay. So these are the things like you can tell this much turbulence is there in the flow field. Okay. And if I am taking the equations, the transport equations, I think you know the transport equations. So I have the continuity equation, okay. Then I have the momentum equation. So and if you try to solve those equations, okay. So finally, what you will find that is, okay, you can do the time averaging and you can solve this equation. So finally, what you will find that you will be having some extra terms for turbulence. This is the regular term what you will be having. So this you have studied in your laminar transport equation. Day before yesterday you have studied. Similarly, this laminar y momentum equation, laminar z momentum equation. What is that I am having extra? So these are all the turbulent terms. So these are all the turbulent fluctuations. Okay. So one thing what we have to note is like whatever the term which we have extra in the equation, what it will be doing. So it will try to alter this equation, solution of this equation. Okay, how it will alter the solution of the equation? That is very very important. Please listen. So here it will, if you are having a laminar profile, if these three terms are not there, these turbulent terms are not there, you are going to get the laminar profile. So it will be like a laminar flow equation. Okay. Now, if I am going to include this equation, include these terms, then I am going to get a turbulent profile. So that means the new terms which you are adding, that the turbulent terms which are adding to that, it will convert my laminar profile into turbulent profile. This is very important. Please try to understand. It will convert these terms. These terms are called as turbulent stresses. So these terms will be present only when the flow is turbulent. When the flow is laminar, all these terms will become zero. When what is the effect of these terms? These terms present in the equation will convert the laminar profile into a turbulent profile. For example, if you are having a laminar profile through a pipe, it will be like a parabolic shape. Okay, but when these terms are included, after that you will be finding that it will be having a flat parabolic shape. Okay, so what is that effect? The effect of including the turbulence in the calculation is that it is altering the velocity profile, underlining altering the velocity profile. So because of that, what is happening? Uh, what is the meaning of changing the velocity profile? If a velocity profile is getting changed, it means that indirectly like viscosity is changed. Again, I'm telling indirectly it means that like viscosity is changed. So that means the effect of the turbulence in the flow field is like changing the viscosity. It is like changing the viscosity. Okay, it is not changing the viscosity, like changing the viscosity. So that means if you want to solve a turbulent flow problem, you have to attack the viscosity. Okay, so what you can do in the viscosity, you take the viscosity and you split the viscosity into laminar viscosity and the turbulent viscosity. Okay, laminar viscosity is the regular viscosity which you have because of the viscousness of the fluid, but you don't have anything called as the turbulent viscosity. We ourselves, we are creating a turbulent viscosity because the effect of turbulence is to alter the velocity profile. So that is why we ourselves, we are introducing a term called as turbulent viscosity. So how I have to calculate it? So go and find out because of the turbulent fluctuation, how much will be the change in the velocity profile, or how much will be change in the turbulent viscosity. Calculate that, you come back and give it here. Okay, and you try to solve this problem. Now you will get the problem which changed the velocity profile. For example, if it is a flow through pipe, it will not give parabolic profile. It will be giving a flat parabolic profile, which you may be knowing. A turbulent profile you may be knowing. So that profile we are going to get. Okay, so that is what we are doing uh, uh, in the turbulence model. Okay, so in the turbulence modeling, so we are not solving the problem. Actually, turbulence is a transient process. You know that turbulence is a fluctuation. So that means the fluctuation means the velocity will be fluctuating, temperature will be fluctuating, pressure will be fluctuating. If you really want to solve that problem, what you have to do? You have to solve that numerically as a transient problem. So since it is a fluctuation, each fluctuation will be having a very small time step. So you have to go small time step and you have to solve a transient problem like what we have seen previously. And if you do like that, okay, and you know in the turbulence we will be having eddies varying from smaller eddies to larger eddies, because in the turbulence you know that actually it is the energy is given from the larger eddies to the smaller eddies. So that is called as energy cascade. Okay, so that is the physics of the turbulence. Okay, so that means from the larger eddies energy will be going to the smaller eddies. So that is what we will be seeing in a turbulent flow field. If you are going to model that, what you have to do? You have to model from the larger eddy to smaller eddy everything. Okay, as a transient problem. So if I model like that, it is called a direct numerical simulation. It is going to be a very big problem. Okay, and sometimes a few people they do the modeling of larger eddies because that only will give structure for the turbulence. Smaller eddies will not give structure to the turbulence. So that is why we are going for modeling the larger eddies. What is called larger eddy simulation. Okay, smaller eddies are just modeled. Okay, But even for smaller problems, okay, where turbulence is not important. For example, in air conditioning problem and all, so the shape of the turbulence, formation of the turbulence, it's not important. Why? Because if I am taking a chimney problem or any other problem or cloud problem, so there that large eddy structure formation, dissipation, uh, that is very important. But for our case, it is not important. It is enough if you know where what is the effect of turbulence in the flow field, how the flow profile is altered, okay, how the flow profile, how the flow velocity is altered. That is what we are interested. So that is why we are going for modeling. Okay, so the type of modeling we are doing, it is called RANS modeling. Just now I told you we have seen K epsilon model, okay, and one constant viscosity model. So both these things, it will do the same thing only. Okay, it will make the it will make that it will model the effect of effect of turbulence in the flow field. It will not go for time varying calculation. Okay, it is very difficult to do that. So that is why in our solver we are finding that only two is there, K epsilon and one constant viscosity model is there. Okay, we are going to discuss about that one. So that means I told you. Mm, Here you can see this is for laminar. You will be using this expression. What we are doing, the viscosity we are introducing for a turbulent viscosity. Okay, where from we are getting turbulent viscosity? From turbulent fluctuations only. Okay, so that means the viscosity for the flow, you can split it into laminar viscosity and turbulent viscosity. So you have to go to this equation, and instead of having this viscosity, okay, you can have the laminar plus turbulent viscosity. Now these terms will not come. When I am giving turbulent viscosity here, these terms will not come. Okay, that we have to know. So now what we have to do, so our job is to just find the laminar viscosity and the turbulent viscosity. How you are going to find the turbulent viscosity? So that is going to be our problem. Okay, so that is why. Okay, so we have to find out the turbulent viscosity. So we are finding the turbulent viscosity indirectly. Okay, we are finding the turbulent viscosity indirectly, and we are going to our equation, set of equations. In that we are giving the turbulent viscosity, and then we are solving and we are getting the solution. And how you are doing that? Okay, for a simple model is the mixing length model. So in the mixing length model, it is not at all used. It is used only in 2D. Okay, but it will help us to understand the problem. Okay, so what is that we are interested? We want the turbulent viscosity. It is given in a form of turbulent kinematic viscosity. No problem. We can put it as mu by rho. From that we can calculate. Okay, turbulent kinetic viscosity is proportional to the velocity scale and the length scale based on the unit. So you can split this as meter per second and meter. So the length scale, okay, so the length scale, it is given as Lm, okay, and the velocity, you can write it in the form of L dou u by dou y. Okay, so this is given by Prandtl mixing length model. So the velocity scale of the turbulence, I can write it in the form of L dou u by dou y. So both put together, I'll be getting L into L dou u by dou y proportional, and we can introduce the constant of proportionality. So while introducing the constant of proportionality, that L square into dou u by dou y can be converted into Lm square into dou u by dou y. So now for finding the turbulent viscosity, what is required? Mixing length is required. So just find the mixing length, insert here, you can find out turbulent viscosity. But this can be used for only 2D problem. For our case, it is not going to help us. Okay. Okay, so that means we have to go for the next problem. So this is very simple, but it will not be useful for us. Okay. Next, we are going for the Spara-Talmaras or one equation model. So in the one equation model, what we will be doing is we will be having a one transport equation for turbulent viscosity. So that means, you know, our transport equation, you will be having transient term, transient term, then convection term, then you will have diffusion term, then source term. So instead of phi, if I'm using turbulent viscosity itself as my parameter, then my equation becomes a conservation equation for turbulent viscosity. Okay, so that means for each node I have to solve this turbulent viscosity. Okay, and if I'm calculating the turbulent viscosity, so that means I have the turbulent viscosity in my hand. Just I have to give this in the equation. You have to give this in the equation set. When I introduce this the turbulent viscosity in my equation, before that it will be laminar. Now if I introduce turbulent viscosity, then it will become a turbulent profile. So from that I can solve that. Okay. So this is called as one equation model. So that what we have seen, constant effective viscosity model, whatever we have seen. So that is what we will be using it. Okay. So mostly it is used in unstructured code in aerospace industries, and it is used for simple models like what we are having now. In building turbulence, it is smaller. Always we will be designing for lower turbulence in the inside the building. So because of that, that makes it simple for us. Okay, simple models itself we can use it for solving the problem. Okay, that is one equation or small turbulence model. Okay, and the next is the K epsilon model. Now, what is K epsilon model? So I told K is the turbulent kinetic energy. So that is what we have seen. And for main flow, you will be know in a boundary layer we will be having main flow. The main flow also will be having the energy. So that is called as turbulent kinetic energy for the main flow. Okay. So the interesting thing is the turbulent viscosity is proportional to the turbulent velocity scale into length scale. Velocity scale is given by root k, because you know turbulent kinetic energy is velocity square. I take root of that, I will be getting velocity. Okay, and this also k also I can in the same way I can find out. So k is given by k power root 3 by 2 divided by epsilon. So when I multiply both, I will be getting k square by epsilon. So the expression is turbulent viscosity, kinematic turbulent viscosity. It is k square by epsilon, and you should have a constant. That constant is not shown here. And here you can see, okay, 1 minute, I'll just show it that, then we'll go to the equation. So nu t, it is C nu into k square by epsilon. So that means if you want to calculate nu t, k square and k and epsilon is required for each node. Okay, how you can calculate k and epsilon for each node? Then you require equation. So that means a transport equation is required for k. So that is for k is so this is the transport equation for turbulent kinetic energy. So this is transient term, this is convective term, this is diffusive transport term, and I have the source term and the sink term. Because you know turbulence is created and it is dissipated. So that means there should be a source as well as sink. Otherwise, what will happen? Turbulence will grow. It will keep on, the shape will be keep on increasing. So that's like that it should not happen. So we have the rate of production, that is a source and sink will be there. Similarly, we have the equation for dissipation also. I have the transient term, convective term, diffusion term, and I have production as well as destruction term. So the thing, we have two beautiful equations. One is turbulent kinetic energy equation. Another one is dissipation equation. So that means we will be having k and epsilon value for each node. Like how you are calculating velocity, how you are calculating temperature for each node, you will be calculating k and epsilon for each node. So when you calculate that, give that value here and substitute the value of C nu, find out turbulent viscosity. You take this turbulent viscosity and you give it in the governing equation. So very simple. If you before that it will be laminar. Okay. Now you give this turbulent viscosity, then it will become a turbulent profile. Very simple. That's how we are doing the turbulence modeling. Okay. That's how we are doing the turbulence modeling in the solver. I think this is sufficient for you, because these are the two things. Okay. So which is used in the models. Okay. So we are using a k epsilon model. One is constant effective velocity model. So that is now what we have seen, one equation model. Then we have a k epsilon model. Okay, so that is a two equation model. Okay, it is a two equation model. So now I think we have discussed about various models. We have discussed about turbulence, what is its effect, and we have discussed about discretization scheme. We know about iterations. Okay, so we know about what is the initial solution. Cell monitor also I told you. So some point inside the domain how you have to do, and the residual display, how many equations we are solving. So that is what is given here. Okay, and okay, so that means fairly you know what are all the terms that are there in the CFD solver in a building energy simulation software. Okay. Okay. So I think this is sufficient. These are all advanced model. Okay, so these are all advanced model. So that is not required for you, and it is for the general purpose CFD solver. We will be using this. Okay, and near wall treatment, how we will be giving boundary conditions. Okay, near the wall for the turbulent solver. So two methods are there. One is standard wall function approach. Another one is two zonal approach. Okay. So you know now we have seen that. Okay. In the turbulent boundary layer. Okay. Your exact solutions will be like this. So near the wall, the exact solution is u plus is equal to y plus. So these are all non-dimensional parameters. So this is what we will be following. Similarly, in the core region, okay, so in the fully turbulent region, so I'll be having log law layer. Okay, so the exact solution will be following log law. So outside the log law, okay, so I'll be having this. This will be the solution. This is also log law, but with some constant will be there. Okay, so whenever you are giving boundary conditions, so near the wall, okay, so near the wall, it is very important. The boundary conditions, it has to be given very correctly. Otherwise, what will happen? The information that turbulent boundary information, it will not go into the domain properly. Mostly, we will be having a wrong solutions because of not giving this solution properly into the domain. So for that, what we are doing, uh, two types of approaches we will be using. Okay, so one is wall function approach, another is two-layer approach. The wall function approach will be having a coarse mesh. Near the wall, we will be giving exact solution. So what is that exact solution? Near the wall, you know that u plus is equal to y plus. So that can happen. Okay, or if it is a log layer, okay, so u plus is equal to 1 by 1 constant into ln e y star. Okay, so what is y star? It is given here. Okay, so it is given there. Okay, so it is okay. So now y plus. Okay, so this is a non-dimensional distance. Okay, one-dimensional distance. U stand is u plus is the non-dimensional velocity. Okay, from the wall. Okay, and we have to give the value correctly. Okay, so if you are taking a coarse mesh, give the exact solution so that the correct information will go inside. Okay, so that is one way of approach. The other one is don't give the exact. If you don't want to give the exact solution, refine the mesh nicely. Okay, and use two zonal k epsilon model. Okay, so k epsilon model, two types of models are there. One is low Reynolds number k epsilon model, and another one is high Reynolds number k epsilon. In the fully turbulent core, we will be using a high Reynolds number, the k epsilon model. Whatever the k epsilon model we have seen now, that we will be using it. That is, in that fully turbulent core, we will be using. But near the wall, okay, we will not be using we will not be using a fully turbulent k epsilon model. Here we will be using, already I told you, near the wall, because of the viscous effect, damping will be there. Similarly, for the k epsilon model also, we will be giving damping. So if you are giving damping, what will happen? So we have seen in the first slide, because of damping, that fluctuation, the intensity of the fluctuation will be reduced or damped. Okay, so that means we will be using two k epsilon equation. For this near the wall, we will be using low Reynolds number k epsilon equation, with the damping function. Similarly, in the fully turbulent core, I'll be using highly turbulent k epsilon model. That is the whatever the k epsilon model, whatever we are using. So because of that, we will be getting the best possible solution when you are going for a k epsilon model. Okay, so you know that okay, the boundary condition for a k epsilon model, it can be given in different ways. So I told you turbulent intensity, turbulent kinetic energy. Okay, or you can give the first case, that is RMS of turbulence. Okay, so there are different ways of giving the turbulence in the flow field. Okay, how you have to give the turbulent boundary condition. So that is what we have discussed now. Okay, so I think I have comprehensively taken whatever it is there in the solver. Okay, so thank you. If there is any question is there, you can ask your question so I can answer. So you can put your questions in the chat box. Yeah, pressure velocity coupling. Okay, so in the, I told you, in the compressible flow. Okay, in the compressible flow, for any CFD analysis, you will be getting interested in finding pressure plot, velocity plot. Okay, and a temperature plot. So if it is a compressible flow solver, then you have continuity equation, 3 momentum equation, 1 energy equation. Okay, so then what and all you can find? You can find out using continuity, transient continuity equation. You can find out density by using x momentum, y momentum, and z momentum. You can find out 3 velocities, and using your energy equation, you can find out temperature. but the pressure you cannot find out using these three partial differential equations. Okay, you cannot find out the pressure. So how you are finding the pressure in a compressible flow? So you are using P is equal to rho RT, compressibility into rho RT. So rho, it is available from the continuity equation, because the first term in the continuity equation is dou rho by dou T. Okay, so if you are solving it transiently, you will find out what is density. Similarly, when you are solving the energy equation, you will find out temperature. So P is equal to rho RT, you can find out. This is for compressible flow. So for compressible flow, there is no problem. When I am coming for incompressible flow, there is no such equation as P is equal to rho RT. We just have uh, uh, the basic equations only. There is no equation. In fact, there is no equation for finding the pressure. So what we are using, so now for the compressible flow, we cannot use the continuity equation because density is constant. Okay, so density is constant in a incompressible flow. So that means we cannot use the continuity equation, but we cannot find the pressure. We cannot find the pressure in the incompressible flow equation because we don't have a transport equation for pressure. So what we are doing, we are using the continuity equation, which is now not usable. Okay, from that I am creating a pressure equation, pressure correction equation. Okay, so what is the structure of that pressure correction equation? It is such that for a particular node or for a particular volume, it will see that when flow is more into some cell, okay, then it will reduce the pressure. Similarly, if the flow is less in a particular cell, it will increase the pressure. Okay, so that is how it will be doing. So what is the meaning? So now I am coupling the pressure and the velocity. And now I am coupling the pressure and the velocity. So because of that, what happens? Okay, so whenever you are solving a problem by simple algorithm, okay, so it will solve the pressure correction. First you will be solving the momentum equation and you will find out what will be the velocities. And when you are giving this velocity into the pressure correction equation, okay, so I'll show you that equation 1 minute. Yeah, when I'm having this equation, okay, so when I'm having this equation, this is pressure correction equation. Okay, P dash is the pressure correction. It is not pressure, it is pressure correction equation, because I'll be having P is equal to pressure is equal to P star gas pressure plus P dash pressure correction. So every iteration I'll be correcting the pressure. Okay, so that means in this, okay, so in this B dash I'll be having the velocity terms because it is from continuity. Continuity you will be doing it by mass balance. In mass balance you will be having the velocity, so that those velocity terms it will be there. So it will be in the form of gas velocities. Okay, it will be in the form of velocities which you will be obtaining by solving the momentum equation in the first step. So the simple algorithm first step is you will be going with the gas values. Okay, for the velocities and pressure, first you will go to the momentum equation only. There you will be solving U star and V star if it's a 2D problem, or U star V star and W star if it's a 3D problem. So that means now first you will calculate what is U star, V star and W star. So those terms it will be there in this term P dash. Now when I am putting this term, okay, inside, now pressure will get corrected. Okay, so if a velocity is more for a particular node, that means this value will be higher. So when this is higher, what will happen? This P dash terms it will go lower. Similarly, the other case is this velocities can be lower. That means P dash, if I give the value of velocities as lower, P dash value will be lesser. When this is coming down, this term P dash will be increasing. That is how we are coupling the pressure and velocity. Okay, if you want to have a detailed discussion, so you can refer to Patankar. Okay, SV Suhas V Patankar finite volume method. or you can refer to Westig and Malala. So they have given the derivation of this pressure correction equation. Okay, or if you want more clearly, so you can join for a separate session on CFD. Okay, so maybe sometimes I may be handling, okay, a separate session for CFD. There we discuss, okay, we discuss this derivation itself, how we are deriving the pressure correction equation. It's a very big equation. Okay, from it will be from the continuity equation. Okay, so from the continuity equation we'll be doing, because a continuity equation is not usable condition in a incompressible flow. We are taking that continuity equation, we are converting that into a pressure correction equation. Actually, pressure correction, it is like a Bernoulli only. Okay, so in a cell, if velocity increases, pressure decreases. Similarly, if pressure increases, velocity decreases. Where it is there? It is in the Bernoulli's equation only. Okay, hope this should have uh, uh, explained your thing. Okay, pressure velocity coupling, or I think a separate. You can refer books. Okay, you can come back also. I can explain you. Okay. Uh, any other question is there? Any other question is there regarding the CFD in the have I explained your question, sir? Kunjan sir. Okay. So otherwise we can have a detailed discussion also. You can join for the separate sessions, CFD sessions. There I may discuss in detail about the derivation itself. So that will be very clear. Okay. But it will take time, very long time. It will take at least 3 hours for this derivation of pressure correction and simple algorithm. Okay. Yeah. I'm telling in the most simplest form. Yeah. Okay. Any other question is there from the participants? So I think I have explained about all the components of CFD solver. Okay, in a building simulation software. I know this topic will be dry because I am taking out and out the concepts, but it will be very useful for you. So rather than without understanding using something, so if you understand and use it, it will be very useful for you. Okay, so I think the time is up. If you ask any question, I'll be happy to answer. Otherwise, we have to close. Tomorrow, we will be having a discussion on the comfort indices. Okay, comfort indices in a CFD. Okay, so using CFD also we can find out the comfort indices. Just now we have seen some comfort indices like a PMV and PPD. So regarding these things, we will be studying tomorrow. Maybe we can have one more session like CFD solving session, how to give the input or separate any significant and separate problem is to be solved, that it can be solved tomorrow, because it is going to be a theory session only. This PMV, PPD and all, it is going to be like definition only, and how it is calculated in the using the solver. That is what we are going to discuss. So that is what we are going to have. And tomorrow is from 6 to 7 we may be having the session. After 7 we will be having a concluding session. Okay, so 7 to 7:30 we will be having concluding session. Okay, so I request everyone to join for that concluding session. Okay, thank you everyone. I don't I'm very see that I don't have find any questions regarding CFD. I think I don't know. Okay, have you understood? All of you, have you understood? Okay. Okay, but the concept is like that only, but I have put in the most simplest form for you. Okay, so if you have any doubt, you can go through. Okay, so you can go through and okay, so you can go through and we will discuss tomorrow. Okay, thank you. Tyagarajan, please put back that feedback link. Okay, Tyagarajan,
Okay, okay, sir. I'm checking,
please
sir.
put back that, or you put it in the group also, no problem. Okay. Here itself you can put it. Okay, you put the feedback link. I think they are saying it is not working. Please check.
Okay.